Hey, how's it going, guys? Hey, those of you guys who are getting into office hours here, if you wouldn't mind on this server, if you would change your nickname to your first and last name, that kind of help me recognize who people are. Also, it sort of encourages people to keep it professional. It's okay, Jerome. We'll survive. Fix your mic, though. Yeah, so I haven't prepared a lecture or anything like that. So I'm just here to answer your questions. I'm sure everyone has very similar questions, but like I said, this isn't going to be a class lecture or anything like that. Hello. Okay, so far we've got how do we start for the multiplexer, and what should Y look like in GTK. So how about we just talk about making multiplexers in Verilog? Does that sound fun? Yeah. All right. So let's do that. Let's get some stuff going. I'm gonna share. we're going to push my Wi-Fi to the limit because we're going to be streaming it here and on YouTube. Wait, I want to change the screen. Cool. All right. Can you guys see the whiteboard? All right. Let's talk about multiplexers. So first off, can anyone tell me what a multiplexer is supposed to do? Hopefully you all can, right? Since you watched the video on multiplexers. Right, so it takes inputs and gives outputs. The best way to think about what a multiplexer does is kind of imagine it as being like an if-else in hardware. So if we draw the sort of schematic symbol for it, which is like this trapezoidal looking guy, imagine that we've got two signals, like A and B, and it doesn't really matter how many bits they are. And we've got an output Y, and we want our system to be able to select between A and B. So we might have, so S stands for select. All right, somebody needs to mute their mic. Okay. So yeah, so we want to be able to select between A or B. And if everything is 1 bit, this is just a 2 to 1 mux. Who is that that's on? Raina, will you mute your microphone? Okay, so we'll wait. Okay, let's get back to it. So 2 1 mux. Basically what happens here is it says that Y is equal to A if S is equal to 0, and Y is equal to B if S is equal to 1. A mux just lets us select between 2 different possible inputs to pass that to our output. Does that kind of make sense? Yeah, so someone's got to say yes. Or type yes. Okay, so how does that translate to the mux that you guys have to make? The 32 to 1. Basically just means that we've got 32 A through B inputs, right? So we've got I0 as an input, I1 as an input, all the way down to I31 as an input. Yeah? So then the selector, to select between 32 different things, has got to be 5 bits, right? Because we've got to be able to do 2 to the 5 equals 32. We've got to be able to count to 32. And the output Y just takes whichever one it is. So for example, if S is equal to, I don't know, 27, then Y is going to be equal to I27. So that's all we're trying to do is sort of select between Y. And that's why for a couple people I've been saying, like, don't get hung up on like what should Y look like in the output, because it doesn't matter, right? It's just going to be whatever you put in I. And we'll talk about that here in a second when we actually go and do it. So let's talk about what goes on inside the multiplexer. So basically what happens is there's a decoder and there's AND gates. So we might have a 5 to 32 decoder like you guys have just made, right? It's going to take a 5-bit input. That's our S. And it produces 32 outputs. All right, we can use a wire for that. That is 32 bits. This first one would be wire 0, and the last one would be wire 31. Let's see. And then the next step is, once you have the decoder, that's the hard part. You just have to have an AND gate for each of your inputs. Remember that if we talked about, just an AND gate going over and taking X, that's Y. Remember that X and 1 is equal to X, and X and 0 is equal to 0. And because we know in a decoder that everything, no matter what value gets put in for S, they will all be 0 except for one of them. Right? Only one input or output at a time will be 1. And so whichever AND gate that's tied to is the one that gets it. So we call this, some of you guys have been talking about, you've done some research online and you've been asking about like what an enable is, because an enable is part of multiplexer. This AND gate business is the enabler, because the AND gates enable each of the individual inputs. So for example, we might have A sub 0, and that's going to be attached to wire sub 0. And I sub 1 is ANDed with wire sub 1, all the way down to I31 is ANDed with wire 31. And then because we only want one of these, we sort of cheat and throw everything into an OR gate. And we can get away with this because we know that a decoder only outputs one at a time, so only one of these will be enabled at a time. And that goes to Y. So that's the sort of logic behind multiplexer. Does everybody understand that? Or does anyone have any questions about this? We'll talk about how to do it in Verilog in just a second. Is everybody good? Does anybody have questions? This is the part where somebody has to say yes or type yes, or say no or ask a question. Okay. You're like, shut up and just get on to the part where you're doing it in Verilog, man. I get it. All right. So let's do a mux in Verilog. Oh, I'm sorry, I didn't hear all your question. Can you start again? Hello? Corey, mute your microphone. I'm going to do it for you. Bam, muted. Okay. So, let's go ahead and do a thing. Let's make a mux. Let's make, I don't know, what size mux do you guys want to make? 5 to 32. Let's make a 4 to 1 mux. Everything that happens here is exactly the same as the 32 to 1. It's just going to be a little bit bigger. So, let's go ahead and make that. Now, our mux needs what in order to be successful? What's the most important part of the mux? Yeah, the decoder. So the first thing we need to do is make our decoder. So for 4 to 1 mux, what size decoder do we need? Yeah, we need a 2 to 4. So 2 to 4, and that's going to take A and D, and we'll end that. And actually, a 2 to 4 is made up of what? Yeah, 1 to 2. So we got to start with a 1 to 2. I'm sure a lot of you guys are already good at this part, but we'll go ahead and do it anyway for completion's sake. So we're going to start by making a 1 to 2 module, or 1 to 2 decoder module. So decoder's got 1-bit input A and a 2-bit output D. And all we do is say assign D1 equal to not A, and assign D0 equal to A. And that's all there is to that. Does anyone have any questions about the 1 to 2 decoder? By convention. So we'll do the test bench here in a second, and I'll show you. We do it to get the output that looks the best. We want to get that sort of descending diagonal line output. So I'll show you what that looks like in just a second. You can make a decoder to do, you can make a decoder to do okay, James, yeah, thanks James. You can make a decoder to go in different directions, but by convention we go from top to bottom. So let's go and make a test bench for this. So screw it, let's just call it test bench 1. Let's be unimaginative about it. Test bench 1, let's add some of the stuff. Timescale, 1 nanosecond, 1 nanosecond. Include, hey guys, make sure you're muting your mics if you're not asking a question. Somebody find that person and make them mute their microphone. Mux 4to1.v. And let's see, module test bench. In module, we're going to use registers for A and a wire for the outputs. So registers for the inputs, wires for the outputs. We're going to pull that decoder module. So decoder 1 to 2. UT for unit under test, attach A and D, and then initial, begin, and end. All right, so now we actually go and create some stuff. We got to create our file to get our waveform. So dump file, decoder 1 to 2 .v, and dump vars 0 and test bench. And then, all right, somebody's got to mute their microphone. It is super distracting. In fact, can we just get everyone to mute their mics unless you're like actively asking a question? All right, so now let's set some inputs. Go A equals 0, delay for 20, A equals 1, delay for 20, let's go back to 0, A equals 0, delay for 20, and we'll put the PowerShell, and we need to create our simulation file. So let's see, verilog -o decoder 1 to 2 testbench.vvp, testbench.v. Oop, it says it doesn't exist. Why is that? Oh, because I called it testbench1.v. There we go. All right. So we've got a syntax error. It says port 2, decoder 1 to 2 expects 2 bits, got 1. That's because this guy is supposed to be 2 bits. Ooh. Oh, good catch, man. I made a mistake earlier today and it does bad things. All right, now we're good to go. VVP decoder 1 to 2 dot VVP. It's good to go. GTK wave. And then a shortcut that somebody showed me yesterday was we can actually just type in the name of the file. 1 to 2 dot VCD when we do the GTK wave command. And it will load with our file. All right, and there we go. So somebody asked me what the purpose was of doing the A0 first, and what we want is this like descending pulse, right? We want the D1, the very first one, to be 1 at the first time, and then the next one to be 1 on the second time. So we want to create this sort of diagonal line that goes from top left to bottom right. Okay, so that's the test bench for the 1 to 2 decoder. Does anyone have any questions about that? I'll probably take some time to read some of these questions. Somebody asked, what is the 0 supposed to mean in dump vars? I'm going to be honest, I actually don't know. I've never gotten more sophisticated than just that. It's just, I've always, dump vars 0, and then the name of your test bench. We can look into that some other time, but yeah, but I actually have no idea. I've never gotten that far into it. It's a function. Those are the two methods that create the waveform file. So this dump file basically says this is what I want to name my simulation file. And in fact, you could name it anything. It didn't have to be VCD. And then dump vars is where do I want to get my signals from. So saying dump vars means, and telling it I want test bench says I want the inputs and outputs from the test bench module. And again, I have no idea what the 0 means. What's up? Yes. But only, so it's worth noting though, we don't really, calling functions isn't a thing in Verilog except in these test benches when we want to run kind of basic stuff. Like these are just functions that give instructions to the simulator, right? They have like no bearing on any like functionality that happens in Verilog. They're just sort of instructions for the simulator. What's up? So it doesn't matter as long as you've got everything covered, right? So we need, the decoder has a 2-bit output. So to connect to it, we need 2 bits of output wire, essentially. Okay. Yeah, so you just got to create a 2-bit something. All right, any other questions about this decoder or this test bench? That's a good question. So why did we do A equals 0, A equals 1, and back to A equals 0? So this is the actual simulation part of the simulator, right? Our input was A, and so we're saying set A to 0, wait a little bit, then set A to 1, wait a little bit, set A to 0 again, and wait a little bit. So when we get that waveform, this sort of lets things happen in time. Notice that we started with A equals 0, and then at 20 nanoseconds, A went to 1 on the waveform, and we were able to view the output. And then 20 nanoseconds later, A went back to 0, and we were able to view the change in the output. So down here where you're actually setting the values, this is where the actual, the simulation part of the simulator comes in. That answer your question? Yeah. So that's where you sort of hit it with stuff and... Oh, what's up? I don't... Can we get the same result using a truth table? I don't understand what you mean by using a truth table. Right. I mean, you could you use a truth table to design it. I guess you could. Is that what you're saying? Yeah. Yeah, so we could have done a truth table for this decoder. And if you go back and watch the actual video on decoders, we do the truth tables for them. But the 2 to 4 is simple enough. Okay. We spent a lot of time on this one, so let's go ahead and go to the next one. We need to actually make the 2 to 4 decoder module. Let's see. So that's got a 2-bit input. So input A is 2 bits. So input 1 to 0A. And the output is 4 bits. So we're going to go 3 to 0 D. I don't know why I tabbed that. And then we need to create 2 instances of the 1 to 2 decoder to make our 2 to 4. So we have decoder 1 to 2. Call the first one U0. And we'll say, actually this one we can just say, so dot A is going to be attached to A sub 1, and its dot D is going to be attached to RD 3 to 2. So the top 2 bits of our output. Oh, actually I'm messing up. Because what do we forget in this decoder? We can't hook them up directly to the outputs. Yeah, we gotta have the wire. So we need to have a 4-bit wire to catch the output from those decoders. So in this case, the decoder U0, its output D is gonna be attached to wire W 3-2. And the next decoder, 1 to 2, U0 is gonna be attached to dot A is attached to A0, and dot D is attached to W 1 to 0, the bottom 2 of that wire. And then the last thing we need to do is the output assignment. So we're going to assign D3 equal to wire 3 and wire 1. And assign D2 is equal to wire 2, wire 3 and wire 0. So notice that we did the first 2 are attached to the top one of the first decoder, and then each of the ones on the second decoder. And so we can, I will copy and paste. Give it assign. Now D sub 1 is going to be attached to wire 2 and wire 1. And assign D sub 0 is equal to wire 2 and wire 0. Okay, any questions about, so that's it for this decoder. Any questions about the 2 to 4 decoder? Oh, somebody said, can I use U2 twice or U0 twice? No, I can't. It's got to be U0 and U1. These are just identifiers. So it doesn't matter what you put, but you're right, they do have to be different. Yeah. The syntax at line 9. Yeah, so basically what happens is the thing that follows the dot is what you are referencing in the module you're pulling in. So, and I know it's confusing here. It'll make more sense when we do the actual multiplexer, because that has variables that are different names. But here, the dot A refers to this A, the A input to the 1 to 2 decoder. And it's attached to A1, which is the first bit of ours. So it's the dot, the thing following the dot is whatever you're referencing in the module that you're trying to make. And then in parentheses is whatever you want to connect it to in the module that you're currently working on. Does that kind of make sense? Yeah, like I said, when we do the actual MUX, they have different names, so it would actually make a lot more sense in that one. But that's the gist of it. And yeah, as Vincent said, yesterday I posted an hour-long video on decoders. So definitely go check that out for much more detail on decoders. Okay, so let's go ahead and make the test bench for this one. We'll try to do it pretty quick. Call this one test bench 2.v. Let me go ahead and add the boilerplate stuff. Timescale 1 nanosecond. 1 nanosecond. Include mux 421.v. Module test bench. In module. All right, regis for my inputs. Now they're 2 bits. So 1 to 0, A. Wires 4 bits, 3 to 0, whoa, 3 to 0. D, the thing we want to test, the decoder 2 to 4, UUT, A and D. Now we actually do the stuff. Initial, begin, and end. Create our waveform file. That's going to be decoder 2 to 4. .vcd. Some of these kids sound very cute, but they're being a little distracting. All right, and then test bench. Now we actually want to do the thing. So A is 2 bits here, so we're going to say A is equal to 2-bit binary 00. Hashtag 20. So delay 20. And now we just kind of want to walk through all the input values of A. So we'll create 4 of them. So we'll go 0, 0, 1, 0, 0, 1, 1, 0, 1, 1. And we're done. So that's the test bench. Any questions about the structure of the test bench? Who is that? Okay. All right, so let's go ahead and run it. We'll bring PowerShell back. Oh, I need to actually shut down GTK wave. All right, so here we go. Verilog-O decoder 1 to 2 dot. Oh no, not decoder 1 to 2, decoder 2 to 4 dot VBP test bench 2 dot V. Look, we didn't mess anything up. So VBP decoder 2 to 4 dot VVP. All right, we got our thing, GTK wave decoder 2 to 4 dot VCD. That kid sounds unhappy, man. Okay, so now we click on the test bench, wire, let's grab our inputs and our outputs, and I can break out the D outputs. So now you can definitely see that like sort of diagonal line of the pulses as the decoder goes from top to bottom. So that's the kind of output that you want to see in your decoder. So any questions about that? Does anyone who know whose mic's on? Because I'm like, scroll. I was gonna say, I don't. Yeah, I don't. I was like, I was looking for the, yeah, for whatever it is, and I can't find it. Hey, whoever. That's toddlers in the system, man. And they went away. Maybe they realized we were talking about them. Whoever his kids those are, they sound adorable. But yeah, they're super distracting, so please keep your mic muted. All right, so that was the test bench for the 2 to 4 decoder. Are there any questions about that or that decoder? And then we can move on to the parts you guys all came here to see. Do we have to do a test bench for each decoder for the mux to work, or is it just a way to check if everything's set up correctly? Yes, you should absolutely do decoders or do test benches for everything. What you don't want is for your thing to be screwed up because of some other little module that you made that isn't working properly. So it's always best to just test at every step of the process. I, as a best practice, even in my own like sort of professional work, I write a test bench for every single module that I write. It's just great practice, even if it is a little boring and tedious. Okay. Anything else? You guys ready to move on to the multiplexer? And our kids are back. All right. I'm going to take that as let's move on to the multiplexer. So closing GTK wave, getting out of there. So we're going to make, oh, we already have it. It's here, mux 4 to 1. Mux 4 to 1. And it has inputs select I and output Y. Module. Module. All right, there we go. So in our 4 to 1 mux, we're going to have the input I is going to be 4 bits. How many bits does the select need to be? Not 32, we're making a 4 to 1 mux. And it's not 4. Let's go back to the whiteboard. Yeah, it's 2. So your select needs to be the same size as whatever the decoder that you need to work with, right? So in this case, in the one that you guys have to make, you need a 5 to 32 decoder, so your select needs to be 5 bits. So in this one, since we're making a 4 to 1 decoder, we're using a 2 to 4, or excuse me, we're making a 4 to 1 mux. I get that messed up all the time. But we need a 2 to 4 decoder, so we need a 2 input select. So it'll be input, 1 to 0, select. And then how many bits is the output? Yeah, 1 bit, right? So we're going to select from all 4 bits of input, and we're going to pick just 1 to pass to Y. And so the output Y is just 1 bit. And then we need a wire. How big does the wire need to be? Yeah, also 4 bits, right? Because it's got to take the output from the decoder. So now we create the instance of our decoder, decoder 2 to 4. The input to the decoder is going to be select. So here's where the syntax makes a lot more sense. It's dot A is attached to select. And the output dot D is attached to the wire. And I need to give it an identifier. What do you do? Yeah, it'd be 31 to 0, but yeah. Yep. But other than that, everything else. No, when your stuff is the same size, you don't have to specify, right? In the 2 to 4 decoder, we had to specify when we were attaching to the 1 to 2 decoders because this input is only 1 bit, whereas our input signal here is 2 bits. So we need to specify which bits we want. So that's why we had to specify here. But up here, we don't have to specify since everything is the same size. When your stuff is the same size, they just stick together. What's up? Why does S have to be 2 bits? Because S needs to match the size of the decoder. So your S, since your input S goes to the decoder, it has to be the same size as the input to your decoder. All right. Any other questions? I mean, yeah. And in fact, I mean, like, and even this last step is pretty similar. I mean, muxes and decoders are pretty tightly like related to each other. Because I mean, we're going to do another sort of AND gate thing here at the end. But basically, yeah, the steps are going to look real similar. All right. So in the last step, if I go back over the drawing, is now we need to add this enable. So we need to add these AND gates to attach to our outputs from the decoder and the inputs. So I'm going to do it the long way, and then I'll show you guys some shortcuts, since y'all's is much, much longer than this. Basically, the way this works is every output wire attaches to its corresponding input. So it's assign y is equal to W3 and I3. Or, because remember we have the OR gate that takes everything, takes all the outputs from all the AND gates and ORs them together, so we only get 1 bit out. So that's OR W2 and I2, or W1 and I1, or W0 and I0. And that's it. Questions about that? What do you got? Why do you want it to be easier? Don't be lazy, just type it out, man. I'm going to show you guys some shortcuts here in a second. But I wanted to show you, like, this is the basic structure right here. So let's go. We're going to test bench this, and then here at the end we'll go back and we'll take a look at some ways to not have to do all that. There are some shortcuts. So no, you don't have to write it 32 times. I did. S is right here. S is the input right here at line 11. S was the input to our 2 to 4 decoder. Yeah. No, it doesn't. Why would you say that S becomes W? I mean, the input insofar in that the input S goes through the decoder and creates W. So I guess if you want to think of it as S becomes W in a weird, twisted, combinational logic kind of way, it does. It gets broken out into its individual pieces. It gets decoded. But does everyone get that? S is the input to the decoder. So why would you put the W on D rather than I being on D? Because W, if we go back to the drawing, W is the output of the decoders, right? And each of those decoder wires goes to an AND gate with one of the I's. Yes. Yeah, you connect it. All right, any other questions about this before we do the test bench? Yeah, keep going back to this drawing. It's those. No, it's fine. It's all good, man. This is what we're here for. That's this business. right? Each bit of I gets ANDed with each of the wires, right? And then all of those guys together get ORed, and that output of that OR gate goes to Y. So if we look at the code here, it's wire 3 and I3, or wire 2 and I2, or, you know, all the way down. That's why. Did that answer your question? Okay. All right, anything else? All right, let's go ahead and make the test bench. So I'm just going to call this testbench.b. And the boilerplate. Time scale 1 nanosecond, 1 nanosecond. Include mux 4to1.v. Module test bench. In module. All right, so we got reg. So what are our inputs? We've got the 4-bit input I, so we need a reg for I. We've got the 2-bit input S, so we need a 2-bit S, and we need a wire that's just 1 bit for Y. Now we create our unit under test, mux 4to1 UT. Make sure I get the order correct, SIY. And then we're ready to do the stuff. Initial, begin, end, create our file. Temp var 0 and test bench. Okay, so now the weird part, right? Because there's, how do we go about testing everything? And the reality is with it, so use a for loop is a way to do it exhaustively. But you don't need to necessarily exhaustively test your multiplexer. You can just put some values in I and then make sure they come out properly, right? So what I'm going to do here is I'm going to say set I equal to 4 bits, and I'm just going to do 0, 1, 0, 1, and delay for 20. Like I said, this, what I picked here, 0, 1, 0, 1, is totally arbitrary. There's no rhyme or reason to it. I just want to be able to see in the waveform that stuff is coming out correctly. So then we'll just go toggle through the select. S equals, what, 2 bits, 0, 0, and delay for 20. And yes, we will talk about some shortcuts for this as well. 3, 4, 1, 1, 1, 1. And that's the end of that. Okay, so questions about the test bench for this multiplexer? So what we're doing is, remember, Y is taking each of these bits individually. So we're just putting like a pattern in that we might be able to recognize in the waveform. So we could pick everything. The important thing is that we cycle through S and make sure that everything is coming out properly. Yeah, so you just want to load a value into I and then run through all the values of S. So let's go ahead and run this guy. Verilog O. It's just the delay. It's we're saying we want 20. We want to do this thing. We want to set I equal to 0, 1, 0, 1, and then we want to wait for 20 nanoseconds. That way, not everything is happening all at once in the waveform. We want to put some time in between our actions. The 4 and 2? What do you mean? Oh, this is the like right here on I equals 4. 4-bit something, that sets the size of the signal, right? Because remember, I is a 4-bit number. We're saying we want 4 bits, and it's been binary, and then what it is. And so the 2 means 2 bits. Okay. All right, so let's keep going. 4to1.vvp testbench.v, and we screwed something up. So let's take a look. Mux 4to1 v. Oh, I did this last time. I do this every freaking time. I've been doing this. I've been making this mistake all. I made a bunch of videos today, and I've been making that mistake all day. Today, and what's weird now is if I were to run the simulator, it would like overwrite the test bench. It gets weird, but that doesn't seem to be the source of our error. So let's go back to line 4. Oh, I forgot the semicolon at the end of the module declaration. Oh, one thing, a lot of people are getting sort of tripped up by this. Note, anytime you see a syntax error and it tells you the line, a lot of times you missed a semicolon. But if you did that, the missing semicolon is going to be at the next command up. So it says, hey, at 4, something is messed up. But if you look at 4, nothing is wrong with 4. What is wrong is that up here at 2, I was missing a semicolon. So you might need to like sort of look up your file, look up your code to find those missing semicolons. I got a handful of emails over the last couple days about that. Okay, all right. So now, what's up? Yeah. Well, then that means you messed something else up, right? Like there's, if I were to like typo out that and run it again, right? Now it says syntax error line 4. So yeah, so syntax error means you messed up some part of the syntax. So if your semicolons are good, so it's like, all right, syntax error line 4, go to the next line up, it's got a semicolon. Now actually look at line 4 to see something is wrong. Okay, so let's do that. Now go VVP mux4to1.vvp, create our output, GTK wave, mux4to1.vcd. All right, let's get good stuff. Okay, so let's take a look at our output and see why stuff is happening. Hey, why do you think these 2 lines are red and X'd out? Yeah, they have no value. They're undefined. And the reason that they're undefined is if we go back and look at our test bench, notice that we never defined a value for S in the initialization. We set I, and then we delayed 20 nanoseconds until we actually set a value for S. And so you can see here, S is undefined, and by extension, Y is undefined all the way up until the 20 nanosecond point, in which case then S got a value, 0, 0, and then Y was equal to 0. Let's actually take a look at I. Yeah, so I is 0, 1, 0, 1. So when S was equal to 0, 0, Y was equal to 0, and that's good. Then we come over here. When S was equal to 0, 1, that's the top one. It's weird that it's flipped over like that. Yeah, so the first one, S is equal to 1. No, that works out. Okay. So that's I2. 8 went to 1. Then on the next one, it went back to 0, and then went out to 1. So we get this toggling effect in our output that shows that our multiplexer is working correctly. There's a lot of work in Verilog that involves just sort of staring at your waveforms and trying to understand what's happening to see that they're working properly. I don't. Does anyone know who this person is? Is it a show or is it somebody having a conversation? Are we eavesdropping? That sounds like. No, it's a conversation. Somebody with your microphone not muted, we're listening to what sounds like a very personal conversation. That's a fantastic idea. We might try that for next time. So this doesn't happen. I'm confused that we can't see like who it is. Like everyone who is visible here. Can I mute everybody and then? All right, I'm gonna try this. Okay, hold on. I'm gonna try to mute everybody right now, and then. Okay, that did nothing. Alright, clearly we need to figure this out a little better. You know what I think the reason we can't see them is because Discord upped their like capacity, but I bet they never actually changed in the UI how many users display here. Well, I muted Corey. Okay, all right, we're gonna power through, and then we'll figure out a solution for next time. Oh dang, that's a fantastic idea. I'm gonna do that. Okay. What's that? You're right. Well, hold on. Wouldn't everyone need to be in that channel to hear me? Or well, then I wouldn't be able to hear questions, which would sort of defeat the point. Okay, we're gonna get through the rest of the session. We're gonna power through, and then like I said, we will get better as we go along, and we'll figure out a solution for this. I bet. Yeah, we can work this out, but we're not gonna do it right now. So, while we seem to have this moment of silence, maybe someone realized that we were talking about them. Who has questions about this test bench or this multiplexer? Anybody? Everybody good? What's that? So I'm doing everything in a different file. Or actually, I mean, we did everything here in the same file. You guys need to do that so that so that way you're not submitting like 5 different files. So all your Verilog code needs to go in the same module and just have one that's, called top here at the top. But But you can make different test benches for your different modules, and you should make different test bench files for your different modules. Yeah, just make sure they're working. All right, what else? Correct. No, we did. We gave a value to I, and then anytime we do something in the simulation, we should wait some sort of delay. Right? Every time you update an input value, you should delay a little bit. Otherwise, your simulation can get messed up. In fact, when it calculates the results, it can get screwed up if you don't delay. Also, your waveform will look unintelligible. So. Oh, you guys wanted to know how to not have to write 32 lines of stuff, right? Yeah. All right. So let's talk about how to do that. Everyone, mute your microphones. Okay. Someone's just like sitting on their microphone. All right. So yeah, so nobody wants to copy and paste out 32 lines. Although there's some people that did it, and those people are heroes. But there's a better way to live your life. So you can create what's called a generator structure. And it starts with a genvar, which would be kind of like our indexer. So we have genvar I, generate, and generate. And then inside here, we'll create a for loop. So before I equals 0, I less than, how many times do we do that? 4. And then I plus plus. Or I actually, as a matter of personal coding style, I hate plus plus. I like to do equals I plus 1. Or plus equals if you can get away with it. But I plus plus works too. And so what we'll do here is actually, we can't just directly assign y because y is only 1 bit. So we need to create an extra wire to hold the enabled values. So we'll call this wire underscore en for enabled wires. And here we'll do assign wire underscore enable I is equal to wi and I little I, semicolon. So that lets you do a for loop. And then here at the end, after the generate, we need to do assign y equals. This part gets a little weird. If you want to OR everything in a signal, you put the operator ahead of what you're ORing. So we'll do OR w enable. And this right here replaces this assignment operator, which for 4 bits doesn't seem like much. In fact, this was more work than assigning for 4 bits. But for 32 bits, that's pretty significant. We needed a place to hold, so we can't, since we have this for loop, everything has to be indexed in the same way. So we can't just directly assign y to equal to these things. It doesn't work that way. So we needed to create something to hold. Essentially, effectively what we created was a wire to hold these results. So this would be our wire underscore enable. Does that kind of make sense? We needed a place to hold these values before they get ORed with y. So that's what that was all about. So yeah, so that replaces the assignment. That's another way to do it. Any questions about that? Can other people see the screen? That might be on your end, I'm sorry. Thankfully, this is all being recorded on YouTube, so you can go back and take a look at it later if you need to. What do you mean? That's running. No, there's. I mean, I'm looking at it right now. It's got 22 concurrent viewers. Hey, you guys on YouTube, can you still see this? Say something in the chat. There's a delay. There's like a 10-second delay. Okay. Yeah, so it's there. Yep. Yeah, so you just go through it 31 times. Oh, you're right. Yeah, it would be less than 32. You're right. Good catch. Or you could do less than or equals to 31. No. Verilog is weird about when you don't and do need semicolons. So one thing I want to. So actually, are there any other questions about this? So if you wanted to exhaustively test it, how would you do that? Okay, you could do a for loop in this. So what we could do is, okay, let's be clever about it. So I is 4 bits, S is 2 bits, so that's going to 615, S is going to 3. So what we're going to do this is we're going to say, I'm going to make an integer. I'm going to call it little I. And I'm going to set it equal to 0. And I'm going to make another one, integer, little s, also equal to 0. And then inside here, I'm going to comment all that out. You can run a for loop. So I can say for I equals 0, I less than, so this is going to index on I, so that's going to be less than 16. I equals I plus 1. Begin and end. And then what would we do? We would say I equals I. And then we'd have another for loop. For s equals 0, s less than 4, s equals s plus 1. Begin and end. S equals less. And then here we should delay for 20. So if you wanted to exhaustively test your multiplexer, this is how you would do it. No, because you need to sort of think critically about. Oh, hold on. Let's see. We actually don't need to change I. I was being dumb here. This is actually a lot simpler than I thought it was. We don't need any of that because we're not iterating on I. We're iterating on S. I stays the same. So we would do what we did before. And just set I. And then walk it through. But no, so the reason S is okay is because we just want to set this number value, right? We want to set S equal to 0, then 1, then 2, then 3. So we're just setting it equal to that integer value. You only need to specify indexes when you care about the individual bits. I'm going to run this and see what it does. Find out what we screwed up. Quit jumping on your microphone. All right. Let's take a look at all of this. So yeah, so it looks exactly the same, just about what we had before, right? So it waits, SI is set to the value it was, and it just walks through. So we didn't actually change anything in the waveform. We just did it in a more expeditious way. What's that? Whoa, that was terrifying. Sorry, can you ask your question again? Well, I did, okay, so I did this thing that was kind of confusing because I thought I had to iterate over I. Yeah, so it's little s. So here I have this would be terrible in real life, right? But I have big S is equal to little s. I could make this more readable by swapping out the little s's with I since I don't need the I. So I do something like this. That's what we've done. That's what this is. I have never tried that. So you're saying, like, don't do... I don't know. Let's try it. Let's see what happens. Maybe this might work. Okay, so let's say we're going to say big S is equal to 0. Big S is less than 4. Big S equals S plus 1. I've actually never tried to do it this way. So let's take a look. That doesn't bode well. The fact that it is now infinitely looping. Okay, so that didn't work right away. Let's go ahead and say, let's specify less than 4 bits, decimal 4. Let's try again. Okay, no, that seems to not work because it's causing it to infinitely loop. So maybe with some tweaking you can get it to work out. But right off the bat, that doesn't seem to work very well. But that does. Okay, any other questions about this test bench? It's up here. Yeah, well, the question was, like, could we just throw the input signal up in the for loop and have it run? Yeah. And the answer to that seems to be no, we can't. Because we don't care about what I is, we just want to see that the bits of I, are getting passed to Y. So we just set the value of I to something arbitrary. And then the important thing is that we walk the counter, or walk the select, the individual bits get selected. So the answer, I guess the short answer to your question is because I is not that important, so you only need to set it once. And then we're selecting from I. Does that answer your question? Okay. All right, what else? If anything at all. Okay. You can use a dip switch. You can use whatever you like. That's not important. What's important to me is that you can, like, toggle the LEDs on and off. Yeah. Okay, before I leave you guys on this multiplexer, since y'all were great and showed up to this, I'm going to show you after some playing yesterday, it turns out that you can actually reduce all of this assignment business down to just one line. We can lose that W enable. Any combinational logic expression can be reduced to just one thing. So we could say that y is equal to ORing all of the results of W and I. And that will work just as effectively. Yeah, so we're doing it. Some people are watching this on YouTube. I did like a YouTube live thing, and then that should be available after this is done. Yeah. So you can go back and take a look at it. Cool. So this is, if we had, let me throw it back real quick. Assign y equals W3 and I3, or I'm going to type this out real quick. I should have deleted it. I2 or W1 and I1 or W0 and I0. So these two lines, line 13 and 15, do the exact same thing. Since we're ANDing all of the bits of W and I together concurrently, right, we can just write the expression as W and I, and all of those bits get ORed together, like by that operator. Yeah. So you don't have to do any copy and paste. You can get it done in just this one line. So the entire decoder, right? So the entire multiplexer can be done just like that. Which means a 5 to 32. So all you would do to do a 5 to 32 is change this to 31. Change that to 4. Change that to 31. Change this to your 5 to 32, and you're done. That's all you have to do. All right, somebody needs to mute their mic. Hearing myself is worse than hearing the kids. Okay, any questions about doing these multiplexers? Because they're, despite the fact that they're both Verilog, they're different contexts. So generate creates a logic expression inside a logic module. When you're just running a test bench simulation, you can actually get away with doing stuff like for loops and stuff sort of on their own. The short answer to that is you don't need generate in test benches. All right, any other questions? Are you asking should y be initialized to 0? No, since it's the output, you don't have to initialize the outputs. Yeah. Right, you only have to initialize inputs. All right. Anything else? We're out of time for today, but I can maybe answer one more question. Again, because Y is someone operating like a radio from like the 80s. Okay. Right, since Y is an output, we in the test bench we only have to deal with assigning values to the inputs. Yeah, and then the outputs respond. That's what we're testing, right? Is to see that our outputs are what we expected. Yep. Yeah. All right. Anything else? Correct. All right. To answer, what's that? Yeah. Let's see. Oh yeah, we've covered some of these. Let's see. We talked about what it looked like on GTK Wave. Is I 4 bits because it's 1 to 4 mux? Well, I is 4 bits because it's a 4 to 1 mux. Justin asks, do we have time to get the mux assignment done over the weekend, or do you want it done tonight? I would like for you to do it tonight. Surely we have talked about enough here that you should have no problem getting it done tonight. But I'm not gonna for the assignments that are due this week. I'm not doing any late penalties for anything like that. So don't stress out about it. And I probably won't grade over the weekend, so don't worry about it. But try to get it done as soon as you can. And then the last question: what is the difference between Genvar I and integer I? They're very similar, but they are different things. Genvar I, a generator variable, works in a generate loop, which is a Verilog specific thing, and an integer I is just that. It's an integer. So you can treat them the same way. It just depends on the context. Integers in test benches and Genvars in your generator loops. Okay. Anything else? So the short answer to that question is yes. There is like we are only scratching like barely the surface of what Verilog does. There is lots of nuance and there's lots of powerful stuff that the language does. As far as what you need to know in order to do your assignments up to this point, no, there's nothing else that there's no other nuances that you need to know about. No, no, no. Everything you got, we have gone over everything that you need in order to get these assignments done now. So, all right. Cool. Well, thank you so much for showing up to office hours, guys. Like I said, I'm doing this from 4 to 5, Monday through Friday. I suspect the ones on a day where something is due will be more popular. But yeah, let me know. We'll try to figure out the audio issue and basically how can we, avoid that. And yeah, I think you're right. So I'm gonna have to go and set rules and stuff, but I'll play with that over the weekend and we'll get it figured out. Yeah. So I will see you guys. Like I said, don't try to get the assignment done tonight, but don't stress too much over it. I'm certainly not going to get around to grading it until Monday or Tuesday, so don't freak out about it. And I'll talk to you guys on Monday. Thank you so much.